what we're doing, we're still trying to understand generic global rigidity in two-dimensional space. And so in particular, we're looking at the sufficient conditions for global rigidity, which we know, which are free connectivity and redundant rigidity. And we're trying to show that every graph that has both those properties can be generated from the smallest such graph by this fundamental one extension operation and edge addition, so some sequence of these two operations. And we've already seen, which was the real sort of technical detail part that I went into the proofs for, that this result is true in the special case where the redundantly rigid graph is a circuit in the two-dimensional rigidity matroid. And then last time, we showed that in general, redundant rigidity for free connected graphs, redundant rigidity can be translated into a matroidal property, that the rigidity matroid is connected. And the matroid being connected means that for any pair of elements in the matroid, there is a circuit that contains that pair. I guess, for example, if the whole graph is a circuit, then clearly this is true, but it's a generalization of circuits. And it's analogous to K connectivity in graphs. So this is R2 connected would be equivalent to analogous to the cycle matroid, so 2 connectivity for just graphs, but you can have analogous higher connectivity versions of matroid connectivity that are analogous to K connectivity, if you like, but that's a bit of a diversion from the content today. And so what we finished the last lecture on Monday with was that we proved that if the graph is free connected and its rigidity matroid, two-dimensional rigidity matroid, is connected, and it's also minimal, so we can't throw any edge away without destroying one of these two properties, then it must be true that the graph has a vertex of degree 3. So remember, we're trying to show that we can always do one extensions and edge additions. So if we to give some big graph in the class, and I can't do edge additions because it is minimal, then I must have a vertex of degree 3 to do a 1 reduction on. So this was a big step forward towards that. And it's not obvious, to me at least, why you would have this degree 3 vertex in a redundantly rigid graph. And we'll see towards the end of this lecture what the number of edges in a redundantly rigid graph in the plane can be, and it's quite a lot higher than you might expect, and doesn't automatically guarantee a degree 3 just from the count. And so having this connectivity condition that guarantees it has got us a big step forward. And in fact, that's the last kind of detail bit we're going to do. We're going to really not do very much else before we're finished. So I'm just going to give a bit of a sketch from here on. Okay. So as I say here, this degree 3 gives us a chance to apply a 1 reduction, and hopefully we can do that to a smaller free connected and R2 connected graph. So just like it was for circuits, there'll be a sort of an admissibility step, preserving R2 connectivity, and a feasible step where you want to find an admissible node that's also preserves free connectivity as well. And so what we did last time to find the vertex of degree 3 was we used the fact that R2 connected graphs have ear decompositions. And so our ear decomposition, say as graphs, was H1, H2 up to HT, say, and we suppose it's not a circuit, so T is at least 2. And then we looked at all of the previous HIs, and that gave us something. And then we looked at the way the last ear, the HT, interferes with the rest of the graph. So it has some set X, where this is the overlap, and some set Y, which is what's in HT, but didn't occur already. Because it wasn't, the graph is not minimal, HT didn't just add a single edge, so it did add at least some new vertices, and then we were able to show there was a node outside. And basically, that's about all I want to say about the general case, because now you sort of have this picture here, which says HT is a circuit, it has a node in it, some vertex of degree 3, we want to do a 1 reduction on that node, and what I'm basically going to say is that we can use the fact that most of this, that some part of HT is this set Y, which doesn't interfere with the rest of the graph, to translate the results we proved for circuits, to apply them to this circuit HT, but find the admissibility and the feasibility apply to the entire graph rather than just HT itself. So we don't introduce any problem that ruins the properties we had for the previous ears in the decomposition as we go. This is not at all obvious if you start trying to prove it, and the theorem that Jackson and Jordan did to prove this takes a lot of effort and it's very intricate, but I don't want to go into the details. I just want you to believe that it can be done using similar techniques to what we did for circuits. Okay, so that's what I say here, that it's similar but significantly more complicated, and I'm not going to go into the details, but here's the theorem of Jackson and Jordan from 2005. If you are a free connected R2 connected graph, and you're minimal in the sense that G minus E fails to be one of the two things, then either you're the complete graph on 4 vertices, or there's a degree-free vertex, a node. We already know that bit, but there is a node such that when we do the one reduction at that node, adding some edge among the neighbors, so one reduction at V, adding xy for some xy in the neighbor set, you can do such a reduction that maintains free connectivity and R2 connectivity. Okay, so this then gives us the recursive construction that we were building towards, that basically now it's a very simple induction argument on what we already know to show the global rigidity theorem. But on the other hand, there are still some little things that I'm basically going to sweep under the rug, so to speak. So one of them is an exercise. So if I take a redundantly rigid graph and apply a one extension operation, it's relatively easy to see that the new graph will have the properties you want. If you are rigid, infinitesimally rigid or rigid, these ones we've already talked about before, but it's not necessarily so obvious that if you take an R2 connected graph, I mean, it's not hard, sort of a couple of paragraphs, but an exercise would be to show that if a graph is R2 connected and G dash is obtained by even an edge addition is not necessarily trivial, or a one extension, then the resulting graph is R2 connected. And so I think I even give a hint for this. So my hint is to think about the R2 connectivity definition in a very slightly different way. So think about it as defining an equivalence relation on the set of edges, saying that two elements, two edges, are related if they're the same, or there exists a circuit containing the pair of them. So it's a very small reformulation of the definition I gave, but if you try the exercise, then the way I see the proof going, transitivity of this equivalence relation will help you to make the proof work. Okay. So with that exercise and what we just said about the reduction step, the theorem you get is the recursive construction theorem, which is here, which says a graph is free connected and R2 connected if and only if it can be obtained from K4 by one extensions and edge additions. And we've already previously seen that K4 is globally rigid. Edge addition obviously preserves global rigidity. And we talked about when we looked at stress matrices, showing that one extension preserved global rigidity as well. So we basically know as a corollary to this theorem, the characterization of global rigidity. But still, I'm going to write it as a theorem and proof just to hammer home the theorem, because I think it's one of the most important theorems in rigidity theory. So you take a generic framework GP in two-dimensional space. Sadly, this proof doesn't work in any higher dimension. Then the framework is globally rigid if and only if there's a trivial case where you're a very small complete graph, because for example, a triangle is certainly not redundantly rigid. If you throw an edge away from a triangle in the plane, it will definitely be flexible. But if you have at least 4 vertices, even if you're complete, it coincides with the other conditions. So, or the graph is free connected and redundantly rigid. Okay, so it's very easy to deal with the case of small graphs. It's just globally rigid if and only if the graph is complete. So we can suppose we have at least 4 vertices. The first lecture we started with global rigidity, whenever that was, we proved Hendrickson's conditions, which showed that in any dimension, global rigidity implies redundant rigidity and D+1 connectivity. So the fact that our globally rigid framework must have an underlying graph which is free connected and redundantly rigid followed from that. For the sufficiency, we start with a free connected and redundantly rigid graph. And we proved last time that for free connected graphs, in fact, for nearly free connected graphs, we don't need to worry about that. We proved last time that redundant rigidity and R2 connectivity are the same for free connected graphs. So our free connected redundantly rigid graph is exactly a free connected R2 connected graph. So the recursive construction theorem I just mentioned that said all free connected R2 connected graphs can be generated by edge additions and one extensions from K4 tells us that if our graph is not K4, then it can be reduced to a smaller free connected R2 connected graph by one reduction or edge deletion. We can go back and, so the way I've phrased it is to avoid using the Gortler-Healy-Thurston theorem because I think that's complicated. So I've expressed it by talking about stresses. So we can use the fact that K4 has a full rank stress. So we checked that in the stress matrix lecture. And we checked that one extension and edge addition preserved the property of having a full rank stress. So by induction, and since we're doing edge additions and one extension sits on the number of vertices plus edges, we can generate a full rank stress for any R2 connected, free connected graph G. And then we showed Connolly's result, which was that if you have a full rank stress, then generically you are globally rigid. And so the final graph at the end of the construction will always be globally rigid because the first one was, and the operations that we used that generate every graph in the class preserved full rank stress and hence were globally rigid. I could have talked about global rigidity directly without stresses by using the Gortler-Healy-Thurston theorem, but I wanted to avoid it because, as I say, I haven't gone into anything of the proof of that. Or I could have used an alternative proof technique that was due to Jackson, Jordan, and Zabadka, where they talked about one extensions without using stress matrices. So again, I could have avoided stress matrices that way, but I thought they were nice and they're going to be relevant to a couple of the guest lectures we have, I think, coming up next week. Okay, so that's the proof of the theorem, and that's basically what the aim of the last 4 or 5 lectures has been. So maybe it's a good time, even though it's early in the lecture, to stop in case anyone has a question.
So Tony, I have a question actually.
Yeah.
So I think, yeah, so Connolly's result shows that a generic framework with a full rank stress is globally rigid.
Yeah.
But you're actually proving, I guess it's slightly stronger than that because it's saying that if you have one framework with one generic framework with a full rank stress, then all generic frameworks will have a full rank stress.
Yes, so in the stress matrix lecture, I gave a result. I don't think I gave the proof, but if you have a infinitesimally rigid realization in any dimension of a graph, and you have a full rank stress, then you know automatically that every generic realization of that graph has a full rank stress as well. So because it was infinitesimally rigid as well, and in the lecture where I talked about one extensions preserving full rank stress, we had this result that, first of all, one extension preserves infinitesimal rigidity at a special position, collinear, and it also preserves full rank stress. And then you can perturb and preserve both properties as you do to a generic location. But more strongly than that, you can also show that all generic realizations will have a full rank stress as well.
I think I must have forgotten that. What's the general reasoning behind that? Is it some sort of algebraic geometry stuff or something else?
If I remember rightly, it's just a case of thinking of rational functions in the coordinates, because the entries in the stress matrix are rational functions of the coordinates in the points, because they come from the co-kernel of the rigidity matrix. And so I think you can just get a violation of algebraic independence if this kind of thing wasn't true. So this is a lemma in, I mean, so you can check if you want that I'm not talking nonsense. It's a lemma in Connolly-Whiteley. They have a paper called Global Rigidity, the Effect of Coning. So they have the same statement I said where they perturb the global rigidity, but they have a slightly easier, so that one uses the averaging technique, but they have a slightly earlier lemma in that paper where they preserve full rank stress as long as you're infinitesimally rigid.
Okay, all right, thank you, cheers.
Okay. Yeah, so this paper is something like 2010, if anyone wants to look at it. It's called Global Rigidity, the Effect of Coning. Although what I said is not relevant to coning, but we'll come to coning on Friday, I think, if I get there in time. Okay, so I wanted to mention one other alternative proof of the characterization, which is due to Shinichi Tanigawa. So he came up with relatively recently a stronger move than one extension, basically, which, well, I won't try and get it exactly right, but it's just a slightly stronger move than one extension, which allows him to make the combinatorics significantly easier. It still uses a lot of the combinatorics that I presented, but it gets around some of the more technical bits that I didn't present, and almost reduces the combinatorial step to finding a vertex of degree free. So still going into the ear decompositions of the R2 connected graphs as we did, but then not having to worry so much about the admissibility and feasibility in general. So there's a nice, it's a paper called Sufficient Conditions for Global Rigidity or something close to that. So this is a nice proof to look at if you like. Yeah, so I've sort of mentioned this about Jackson-Jordan's Abadkar already, but I also want to mention another result from Shinichi, which is a different sufficient condition for global rigidity from the same paper. So we talked about redundant rigidity in terms of edges. So if you delete an edge, you should still be rigid. You can alternatively think about redundant rigidity for vertices. And so there was a talk like on this sort of topic at the workshop a couple of weeks ago. The idea is that a graph is vertex redundantly rigid if for every vertex in the graph, throwing that one vertex and all its incident edges away maintains rigidity. So, for example, if you have a very high degree vertex, it's quite a strong condition saying that throwing it away, you don't lose the rigidity. But given this condition, Shinichi was able to prove that all vertex redundantly rigid graphs are globally rigid in any dimension. So I think this is a nice result. I won't go into any of the proof, but I just wanted to flag up the result for those of you interested. Okay, so we've talked about two-dimensional global rigidity. Want to say a little bit. We already showed that there exist K55, for example, in 3D as an example of a four-connected redundantly rigid graph, which is not globally rigid. And I mentioned a couple of references for higher dimensional families of examples where those Hendrickson conditions fail to be sufficient. But there are some special cases. So I thought, like we did for rigidity in 3 dimensions, I would just point out at least one special case where we understand global rigidity. So in the special case is triangulations of the sphere or maximal planar graphs. At least this is the one I'm going to flag up today. So this is a recent result of Tibor Jordan and Shinichi Tanigawa. So what we saw several lectures ago now was that if you're a triangulation of the sphere, you have exactly 3v minus 6 edges, and you will be minimally rigid. And this was a vertex splitting proof that we went through. But if I take such a graph, a maximal planar graph, and then I add a set of edges, so the set of edges you add to your maximal planar graph will be called braces, and I'll call the graph resulting from adding these edges to a maximal planar graph, I'll call it a brace triangulation. Okay. So clearly we need to satisfy Hendrickson's conditions. So our brace triangulation has to be 4 connected, d plus 1 connected in 3D, and it has to be redundantly rigid. But it turns out if you just make your brace triangulation 4 connected, then it will be globally rigid in 3D. And this is one reason this is interesting is because, as I say, when we talk about maximal planar graphs or triangulations and rigidity, it tends to boil down to showing vertex splitting preserves rigidity, which Walter Whiteley did in the 80s, and then showing that you can get everything in some class of graphs by this vertex splitting operation. But it's still open in general, even now, whether vertex splitting preserves global rigidity. So let me draw a picture. So the vertex splitting operation, in case you've forgotten, looks like this. So I had some vertex in the middle, let's say U, and I want to split it into U dash and U double dash. So these two special neighbors, say V1 and V2, become adjacent to both. There's an edge between U dash and U double dash, and then the other neighbors of U are split in some way among the two. So this vertex, if you forget these two neighbors, would have degree 3. So I have to say the vertex split is non-trivial in the sense that out of these 5 guys, or however many neighbors there are, at least one goes on each side to prevent just having too low a degree to have a chance of being globally rigid. But it's conjectured that as long as the vertex split is non-trivial in that sense, that it preserves global rigidity. And so in this paper, they were able to prove this is true in a sufficiently general special case to confirm this theorem, but it's still open in full generality to show that this always takes one globally rigid graph to another globally rigid graph in free and any higher dimension. Okay, so redundantly rigid graphs. So again, it's a good time if anyone has a question, but if not, I'll spend the next maybe 20 minutes talking about redundant rigidity in 2-dimensional space. Okay.
Tony?
Yeah.
I have a bit of a question. So we've spent a lot of time trying to figure out when graphs are rigid. Is there any interest in the community in trying to understand kind of the degree of freedom of various flexes? I mean, you could imagine, say, kind of trying to cut up the remaining non-rigid cases into some classes and characterizing those.
So we're interested, well, at least so far in the course, we're interested in generic rigidity. So when, for example, we give the Leman theorem or the Polychek-Geringer theorem in 2D, which said minimally rigid if and only if this counting condition, which I can't remember what I actually called it, but let me call it 2-3 tight, this E equals 2V minus 3 condition, etc. And so this also characterizes independence. So the minimal rigidity is the case when the rank is equal to 2V minus 3 and the rows of the matrix are linearly independent. But the theorem as well, it sort of, maybe I'll go over here to have a bit of space. The theorem is automatically a bit more general than that and says that the graph is independent if and only if it's 2-3 sparse. So if and only if you have at most 2x minus 3 edges for all x greater than or equal to with at least 2 elements. And so what that's saying is if I give you a graph that happens to have, say, 2v minus 20 edges, if it satisfies the sparsity condition, then we know it's got exactly 17 degrees of freedom. So there'll be exactly a 17-dimensional space of infinitesimal motions. And so in some sense, by understanding the rigidity, you get this independence. And so you understand the sort of dimensions, at least in the linear algebraic sense, of what the motions are generically. So in some sense, we are doing the same thing. We are doing what you asked at the same time, but I guess you're more interested in the case, actually understanding what the configuration space looks like as a variety. And there it's probably more interesting to think about the non-generic case. And so if you take the word generic out and then maybe you to look at graphs, say you're in the plane and you look at graphs that do satisfy the combinatorics, but have some flexibility, and when do they have a nice motion, when do they have a nice configuration space with cusps or singularities that are of interest, and that's a whole different ball game to the generic theory we've done so far.
Okay, that's it. Great.
Thanks. Okay, any other questions?
Yeah, just to follow up on Will's question. So if you don't satisfy that sparsity condition, then you don't necessarily know.
So you're talking about this thing I was saying?
Yeah.
Yes, so say I give you a graph with 2v minus 20 edges, then if you don't satisfy this condition, then the rows of the rigidity matrix are dependent. But you can check from how much of a maximal size spanning subgraph does satisfy it to still know that you'll have at least 17 dimensions of flexibility. I don't know why I've picked 20 and 17. This is just a random number. But each dependence will give you one more. And so you'll still be able to count how many degrees of flexibility you have. But I mean, I'm not telling you anything about what it looks like. Even in a very small, simple graph, I wouldn't be able to tell you what precisely the topology or anything like that of the configuration space. All I'm doing is looking at the linear algebra, the dimensions of the kernel, etc., of the rigidity matrix, and saying that there must be this much independent flexibility.
Okay, and but then to determine that, you'd have to look at what subgraphs are sparse in this sense.
Yeah, so I guess I mean the co-kernel of the matrix will tell you the dependencies. So you'll know the rank will tell you. I mean, from the dimensions of the kernel, the co-kernel, and the rank, you basically get in some sense, the information to know something. But then you probably, like Will, would be more interested in deeper algebraic properties of what's going on in for those graphs, and that's something this theorem doesn't tell you much at all about.
Right. Okay. Thanks. Oh, I did have another question.
Sure.
A really long time ago, you mentioned that R2 connectedness is just a special case of like a matroid connectedness type condition, and I was wondering then, does that matroid connectedness condition get decorated with a number of, like in this case 2, because we have 2 edges?
Sorry, so there was a lot of banging of drilling above my head, but I think you asked about generalizing this. So the first sort of simple generalization is I've always picked one particular matroid here, so that's a trivial generalization to other matroids. But I did say that, so if you take a general matroid, then M connected, as I defined, is the sort of natural equivalent of a graph being 2 connected. You can have a sort of, I don't know what even to notate it. Let's say KM connected, whatever that means, which is a natural generalization of a graph being K connected. And it is something like the number of edges within each common circuit, but I don't know the precise definition off the top of my head to look at it. There is a paper in Rigidity about highly connected rigidity matroids by Victoria Kazanitsky, who I'm going to have to apologize for misspelling her name. Oops, I was in red. No, I'll get there at some point. Nitsky, something like this, plus maybe Chabakirai or maybe Tibor Jordan, but it's something like highly connected rigidity matroids. And so they go into whatever this actually is. So if you're interested, that would be a place to look. And hopefully that answered enough of your question, Alex.
Yeah, that was my question, basically. Thanks.
Okay, so in the hope of getting through it this lecture, let's continue. So I want to talk about redundantly rigid graphs. So it's obvious if you're minimally rigid from the rigidity matrix, you have exactly E equals 2v minus 3. If you're globally rigid, you have at least 2v minus 2. If you're redundantly rigid, you have at least 2v minus 2. But it's not so obvious what an upper bound on the number of edges in a redundantly rigid graph is. But I want to use the fact that we understand a little bit now about R2 connected graphs to prove an upper bound on how many edges a redundantly rigid graph in the plane can have. Okay, so obviously redundantly rigid graphs, complete graphs satisfy it. You can just keep throwing in edges. So to make sense of this, I need to include this word minimal. So a minimal redundantly rigid graph is a redundantly rigid graph such that if you delete any edge, you fail to be redundantly rigid. So that it's like the minimal rigid graphs, the minimal version of redundantly rigid graphs. We know we have to be redundantly rigid, so we need at least 2v minus 2, but how big can we get? Okay, so first of all, I'm going to solve in this lemma, I'm going to solve the problem for R2 connected graphs. Okay, and I think this lemma, at least in my head, is due to Tibor Jordan from 2014. I should have checked if it goes a bit earlier, but that's the reference that I used. So take a minimally R2 connected graph. So minimally meaning if I delete any edge, it fails to be connected, R2 connected. Then the number of edges, remember we're in 2 dimensions, but the count is what you see for 3D rigidity. The number of edges is at most 3v minus 6. Okay, so let's prove this. We saw last time that every R2 connected graph has an A decomposition. So let's let the ears of the decomposition be the circuits C1 up to CT. And we're going to do induction on the number of ears in the decomposition. If T equals 1, then it's just a circuit. There's only the one circuit. We know circuits have 2v minus 2 edges. And since we may as well assume, I may as well have assumed up here that V is at least 4. Well, in fact, V is always at least 4 because it's R2 connected, so it must be redundantly rigid. So we know this. And having at least 4 vertices tells us that 2v minus 2 is at most 3v minus 6. So the conclusion is true in the special case where there is exactly one circuit. Okay. So we can suppose our A decomposition has at least 2 elements, and our circuits as edge sets were C1 up to CT. Let's let H1 up to HT be the graphs, the R2 circuits of G induced by these circuits in the matroid. Okay, so I'm going to use a fact, which I'll leave the proof as an exercise. So I define the subgraph of G induced by the first S ears. So in particular, I take the first S ears H1 up to HS, take their union and let G dash be that union for some S between 1 and T. Then the fact is that this is a minimally R2 connected graph. So there's this is an exercise, so I won't say much about it, but basically it's sort of like the fact that partial A decompositions can be extended to full A decompositions. So I take my A decomposition C1 up to CT. If I just forget the last one, the previous part was an A decomposition of a smaller graph. And if I forget the last 4, the first however many was an A decomposition as well. So I'll let you confirm that for yourself if you want. But the upshot of the fact is, and by the induction, is that if this G dash is, which is the union of the first S ears, if I call that V dash E dash, then I have the bound we want for that particular subgraph, okay, by induction. So what we need to do is look at the last one, basically. So let Y be the vertices of the last ear minus the vertices that exist in the first T minus 1 ears. And we need to work out that adding this on is still going to give us the right count we want for G. So now we have to use a lemma we had last time, but I haven't repeated, so apologies if it's not quite so clear. But with one of the lemmas said, if Y is empty, then actually by the third E decomposition axiom, all you're adding in the last lobe is just one single edge, and hence that last edge is redundant because you take it away and you go back to a smaller R2 connected graph, which would contradict the minimality we'd chosen. So we know that Y is not empty, and hence by the same lemma we have, wherever it is, we have that the lobe has this size. But we'll use that in a second. So now that Y is not empty, we know that the number of edges is at most the number of edges we had in the first T minus 1 ears, plus the number of edges we add in the last ear, the edges in the last ear that weren't in the existing ones. We know that the number of edges here, we know that was equal to 3v dash minus 6, but v dash is really the number of vertices in the whole thing minus y. So remember, we have our union of the first however many ears, the first T minus 1 ears, and then we have the last bit. X was the intersection and Y was the new bit. So the vertex set here, which I'd called V dash earlier in the proof, is really V minus Y. So it's everything but the new bit here. So that was just from here. CT tilde, as I just said at the bottom, from the same lemma I was mentioning earlier from last time, is equal to 2y plus 1. And then it's easy because I'm putting an inequality to see that if I put the 2y in here, the 2 and the 3 difference cancels out this and we get the inequality we want. And hence we've shown that any minimal R2 connected graph has at most 3v minus 6 edges. Okay. Okay, so then the theorem is to give the same bound for minimally redundantly rigid graphs. Okay, so again, this is due to Thibault-Jourdain. So you're minimally redundantly rigid in 2 dimensions. So probably I should emphasize again that this is in R2. Then the number of edges is at most 3v minus 6. And as I say, this is kind of why I think it was important to emphasize that the decomposition stuff found us a vertex of degree 3, because if you're a graph that meets this bound, which I'll show you, you can do, or at least you can get very close to for large families, then this bound is close to saying the average degree is nearly 6. So finding a vertex of degree 3 is not obviously going to be possible, but the special structure of 3 connected redundantly rigid graphs allowed us to do that. In any case, we want to go into why this theorem is true. So I'm a minimally redundantly rigid graph. If I was just R2 connected, I could just apply the theorem straight away. So suppose I have some number of R2 connected components, so the maximal R2 connected subgraphs, and let's call each of these Q components GI equals VI EI. Okay, so here's an obvious statement to get us started. Since I'm redundantly rigid, the rank of the rigidity matrix is full. It's equal to the 2v minus 3 for any generic P. And now I'm just going to multiply that by 3 over 2 to turn 2v minus 3 into 3v minus 9 over 2. You'll see that just is going to help the calculations in a moment. Okay, so I'm going to use this little fact for matroid theory, that if you have a matroid on ground set E with independence condition I, and you take the components, like the M components in the matroid M, like the R2 components, E1 up to ET, and you take the rank function R of this matroid, then you can express the rank of the matroid as the sum of the ranks of each of the components. So our rigidity matroid has this rank up here, and I'm going to express 3v minus 9 over 2 in terms of the sum of the ranks of each of the Q R2 components, GI equals VI. Okay, so that's exactly what I do here. So the rank of the rigidity matrix is equal to the sum of the ranks of each of the components. And so each of the components were R2. Well, in fact, I haven't quite done that yet, have I? Oh. I guess I got confused. Oh yeah, that's true. So I'm using this, but for each of the components, what I'm doing is replacing the vertices, really, right? So E equals, so am I being silly? Why is this equality true?
Is this the rank function in the rigidity matroid?
Sorry?
Is this the rank? Are we applying the rank function in the rigidity matroid?
Yeah.
So that would be the rank the generic rigidity matrix, which
yes.
is 3v over 9 minus 9 over 2, and then.
Yes. So we definitely took this and replaced the rank with this one.
Yeah.
I want to apply this to say that this is equal to this, but I'm just being, it's true.
So these are the rigidity matrices of the induced subgraphs, right?
The components. But those should be generic too. Yeah.
Yeah.
So what I'm really doing is saying the rank of this whole thing should be equal to the rank of this K4 plus this K4 plus this K4 for the free components. So I missed a, was it Will? Was it you that made a comment there?
Yeah, well, I was just saying that the components are generic too, right? So then you're
oh, so you're just applying this to each of the different components and getting the same.
right. I mean, the real question is, why is the rank break up on the what is the rank of the rigidity matrix break up onto components in this sum-like fashion that you've got R of E equals the sum of R of EIs?
Yeah, so this is a matrix theory fact that I'm taking for granted, but
okay.
I
Then
thought
think it just follows.
So you're saying I don't need that to give this equality, and that's what's confusing.
No, I think you need it, and then I think you just plug in.
Oh, you're right. So sorry for this delay, everyone. So this is RE, and this is RE, sum of REI.
Yeah.
Yeah. So I'm sorry. This was just me being silly. So what I was worried about is I didn't seem to be using this, but I am. Okay. I wonder if Christoph can do some fancy editing to the video, or you can all just watch me struggle if anyone rewatches later. Okay, so hopefully everyone's now happy with this equation. And then the next one's obvious because I've just took 9/2 outside the sum, so I times it by Q. Okay. And now I know from the previous lemma that EI is at most 3VI minus 6. And so I can replace 3VI with EI plus 6. Yeah, so that's what I say here was just justifying this part. And so now I'm going to continue with this, but all I'm going to do is take the 6 out. So 6Q, which is really 12/2Q minus 9/2Q is 3/2Q. And then every edge was in some component, some of M connected, some R2 connected components. So the sum of the EI is equal to E. And hence we can rearrange. So we have this thing, which if we go up is equal, equal, less than or equal to, equal, equal this thing. I think that's where we're going to, yeah. And so we rearrange and say E is at most the 3V minus 9/2 we had there, minus the 3Q/2 that's here. And then these 9 and 3 give me minus 12 over, sorry, well, if Q is 1, but Q is obviously at least 1, and so another inequality gives me the minus 6 I want to finish the theorem, lemma, whatever it was we were proving. Okay, so I got lost in that, but did everyone manage to follow? So we were proving minimally redundantly rigid graphs have at most 3V minus 6 edges. We looked at all the possible R2 connected components, and we used our basically just a standard fact from matroid theory that I was omitting and asking you to believe. And we used the lemma before, which told us how many edges an upper bound on the number of edges in an R2 connected component, and then just did some calculations. And it came out with the number we wanted.
Could you repeat the standard fact from matroid theory?
Yeah, so it tells us that if you take the rank function of a set, then you can express that as the sum of the rank functions of each of the components in the. So these are the matroid may not be R2 connected itself, so the graph of the matroid may not be, but it will have some number of R2 connected components. It might be that some of these are just single edges that don't really go into any component otherwise, but you get that this equation happens. So I guess my first direction would be to this reference to see where. I'm not sure if Tibor proves it or if he references this off somewhere as well, but maybe it's not so hard to prove.
And the components E sub I, they have to be R2 connected.
Yeah, or single edges if they're not.
Okay.
Oh, I've gone too far. Yeah. Okay, so I thought I'd try and get you guys thinking a little bit. So can we achieve this 3v minus 6? Is basically a little thing I wanted you to just to think for a minute about. So we know you need to have at least this, which is satisfied if you're a circuit. And we know K4 can be achieved because it is achieved for the very smallest one just by chance. But that's because K4 satisfies both this and this. And obviously as V gets larger, this one gets much, much bigger than this one. So is it possible we could actually do better than 3v minus 6 if we assume that V is large? So as I say, if you want to have a think for 30 seconds or so and see if you can come up with anything, and then I'll show you some examples.
Would it be true that if you took something that was minimally rigid in 3D with a vertex of degree 3 and then considered it in 2D? So I think that would be redundantly rigid, but I don't know if that's I don't know if that would be minimal actually thinking about it. So
Yes.
Yeah. Well, no, forget it. Sorry.
If you're minimally rigid in 3D, then you're free connected.
Mm-hmm.
It's not so obvious you're going to be redundantly rigid down a dimension, though.
I think that would follow from Gortler, Healy, and Thurston's second result in their paper. They show global flexibility implies, I don't know if that's a good term, not globally rigid implies not rigid the dimension above, I think.
Yeah. Yeah, and so then what you said, the minimality suddenly becomes...
Yeah, maybe it's not minimal though, because you're looking for minimally redundantly rigid, aren't you? So that's strong.
Yeah.
Okay. Yeah. Sorry.
So what's a specific
good question, actually, though? I like that. If you take something that's minimally redundantly rigid in 3 space and you project it, do you automatically get something that's got some redundancy in the rigidity? Is that forced on you? It's not at all clear to me.
If it's minimally rigid in 3D, then I think Sean's saying from a Gortler-Healy-Thurston result, it will be redundantly rigid in 2D.
Redundantly rigid.
If you're redundantly rigid in dimension D, you're definitely going to be redundantly rigid in dimension D minus 1 or anything lower.
It's not a completely trivial result. It's not just immediate. Oh, sorry, I had an Amber alert or something. Yeah, so I don't think it's immediately obvious. But yeah, I guess it's the minimality is the problem. I don't know if you would keep, I don't know if you'd be minimally redundantly rigid when you go
in the
down.
projection.
Yeah. Maybe if you're like planar or something, I guess. If it's like a triangulation of the sphere and you flatten it out, maybe that's true.
Well, that we can draw one of, I guess. We can just draw a simple one. So there's a triangulation of the sphere. So think about that in the plane. Surely I can throw an edge away and still be, oops, I just wanted to throw 1. This is probably still redundantly rigid, isn't it?
Yeah, I think you're right. That might even be globally rigid.
Yeah.
Yeah, so yeah, no, I'm wrong then.
Yes, you don't get the minimality, unfortunately.
Huh. Interesting.
For 3 anyway, there must be some condition maybe guarantees it, but I guess if you're large enough, I don't know. Anyway, since there's not that long left, maybe I can show you an example. So the example that I was going to show is the family of complete bipartite graphs with one part of size 3. So first of all, k free is even independent, so we have to go at least 4. So I've got some x's and some y's. K free 4 itself is a circuit, so you can check that the number of edges is 2v minus 2. It's got 3 times 4 edges and 7 vertices, so that's easy. But what that means is that if you're k free t for some larger t, then you're definitely going to be rigid because the Lemans theorem will apply, and every edge is going to be in some copy of k free 4, so in some circuit, and so you're going to be redundantly rigid. So this is relatively easy to check as a nice redundantly rigid graph, but it's a special kind of redundantly rigid graph because every single vertex down here, all of the yi's have degree 3, and every edge is incident to one of the yi's. So if you take any edge away, you get a vertex of degree 2, and hence you're not redundantly rigid anymore. So every edge is needed for it to be redundant, so it's minimally redundantly rigid. So this is a family of minimally redundantly rigid graphs, but notice that k free 4 had 2v minus 2 edges, but if I add one more vertex on into the part of size 4, it has 3 more neighbors, and so I sort of go from 2v minus 2 to 2v minus 1, and then when I add another one on, I go to 2v plus 0, and then I can keep going. So if I keep the scalar as a 2, each time t goes up, I just add 1 to the constant each time. So I get 2v plus something. I have to think about how that works as a 3v minus something count. So this is what I said about the minimality of k free t. So how many edges does k free t have? Free t, and it's got 3 plus t vertices. And so you can see relatively easily that means it's got exactly 3v minus 9 edges for large t. So this is a family of examples that gets somewhere close to the 3v minus 6. It's only 3 edges away, and it could be very large. And in fact, what Tibor was able to show is that 3v minus 9 is a bound. So you can improve the bound I gave from 3v minus 6 to 3v minus 9, as long as you look at graphs on at least 7 vertices. Okay. So there's a small exercise, if anyone wants to get comfortable with very small redundantly rigid graphs, is to check what happens on 5 and 6 vertices, what happens in the middle. So K4 is the unique redundantly rigid graph on at most 4 vertices. If you have at least 7, then you have this better bound, which is achieved for bipartite graphs, K free t of any size. But on 5 and 6 vertices, what happens in the middle? I didn't do the exercise myself, to be honest, but it's just checking a finite number of small things. So you could try that if you like. If people are willing to bear with me for the last 5 minutes, I want to mention one more result, which is a bit different flavor, but it is just to finish off talking about global rigidity in 2 dimensions, essentially. Okay, so again, this is a result from Bill Jackson and Tibor Jordan. And what it says is if the minimum degree in your graph is sufficiently large, then you're globally rigid. Okay, so we're going to take a graph on at least 5 vertices, and we're going to suppose the minimum degree is at least n plus 1 over 2. So the minimum degree is just about half the number of vertices, and that's enough to guarantee global rigidity. And the proof, which I won't go into, I'm just gonna give you a very quick comment about it, is to show the conditions we've been proving to show redundant rigidity and free connectivity. One of those is easy. So to show free connectivity, here's another exercise for anyone who wants it. And this is actually a lemma from my 3rd year undergraduate graph theory course, which says if the minimum degree in a graph is at least this, whatever that is, then the graph on n vertices must be k connected. And obviously for free connectivity that they want, you just plug in k equals 3 and you get n plus 1 over 2, which is exactly the degree bound in their theorem. So applying this elementary graph theory result tells us that the graph will be free connected. And so all that remains is to show that this condition guarantees redundant rigidity, but I will leave that out. But I think it's kind of nice to have these sort of results that guarantee global rigidity or guarantee redundant rigidity, because they're not the simplest combinatorial properties. And so having simple combinatorial things like this and other results exist are kind of nice, I think. So next time on Friday, what do I plan to do? It's going to be the 12th, isn't it? So yeah, so on Friday, I plan to return to rigidity rather than global rigidity, but I want to start thinking about non-generic rigidity in a certain sense. So I'll talk about frameworks in three-dimensional space that are embedded on the sphere. So I'll talk about frameworks on the sphere and do this by what's called coning, which we talked about a bit. And if I have time, I'll talk about vertices that aren't just free to move wherever you like, but they're pinned or they're restricted in some way to a smaller dimensional, say an affine subspace. So we'll get into that kind of topic from Friday. Does anyone have any questions before we finish for today?
There's a question in the chat.
Oh, yes. Let me just. Do we require that removal of any edge gives a, I guess red is redundantly rigid graph?
So like when we say redundantly rigid, we say that if you G minus NEE is rigid still, right?
Yeah, so it's redundantly rigid if G minus E is rigid, but it has to be true for every single edge. Yeah. So you look at G minus E, G minus F, and so on, and they all have to be rigid.
So for minimally redundantly rigid, is it still for NEE and E?
So for minimally redundantly rigid, yeah. So let me write it. So G is minimally redundantly rigid if G minus E is not redundantly rigid for all edges. So every edge you pick has to be needed to make it redundant.
Yeah. Okay. Thank you.
I had a question. It's kind of a dumb question, but is it possible to characterize the graphs that are both rigid and also have rigid complements? So they can't have too few edges, but they can't have too many edges either.
So by rigid components, are you happy that this is a rigid component of this graph?
Sure.
But I guess you're not happy that this is a rigid component.
No, so all I'm asking is the G and G complement.
Oh, the complement.
The complement of G should both be rigid.
So I've never thought about this. So the complement meaning you take, or say if this is the graph, then the complement is this one.
That's right. Yeah.
Yeah. So, I mean, we know the number of edges in G plus the complement is the number of edges in the complete graph. Mm-hmm. And say we're in the plane, then they both have to be at least this.
Right.
So probably you can do some trivial counting to get an idea of what might be possible. I've never tried this.
Yeah. I mean, I just did exactly what you did. Kind of a quick thing. If we require equality, if we're looking at like minimally rigid G and minimally rigid G complement, you can't find such a thing. But if you allow yourself a little bit extra flexibility, it strikes me that we maybe could find such things. And in fact, it might even be pretty almost kind of ubiquitous if you had V really large.
So you're saying you can't have minimal for both, so that this equation has no solutions. No
That's right.
Solutions. Yeah. Okay.
Or no integer solutions anyway.
No integer.
Yeah. That's.
Yeah. So I guess I mean, so 2v minus 3 is so much less than this, the number of edges in the complete graph. So if you're sufficiently big, it's probably likely that both G and its complement are if you just put one down at random. I mean,
That's right.
but I mean, that's just talking about the total number of edges. We're checking that they're also sparse.
Yeah.
Yeah, I mean,
It's a bit
to be
amusing.
honest, I'm not sure what it would be useful for, but it's kind of a fun little question.
Right.
So it might be nice to establish.
Yeah, I wonder, there may be like the first case where you can get such a thing, may turn out to be something that you can actually classify. I'm not sure what number that would be, but whether like you need v equals 8 or something like that, or whatever, to be able to even possibly get such a thing. But then once you do, maybe there's not that much room.
So probably the one-dimensional question, because there what you want is
good
that
idea.
each graph to be connected. That's probably been studied, and probably in the trivial undergraduate results somewhere, saying some condition that forces G and its complement to both be connected.
Huh.
It fails me immediately what it would be. Yeah, I should get rid of this because I thought you said component rather than complement, so I was just being silly with my answer there. But yeah.
Oh, Alex's comment is a good one too. Might be interesting to consider how many rigid graphs a large complete graph can be partitioned into. That's actually a lot closer to the thing that we just scribbled out.
Yes.
Anyway, kind of amusing. It just occurred to me during the talk, and I thought, I wonder if
Yes.
this is. No.
So for Alex's comment, I mean, if you go to one dimension, then there are results, sort of easy results, talking about decomposing complete graphs into two factorizations, say, and so into cycles, into Hamilton cycles. So they would all be rigid on the line, but into two-dimensional rigid things, say, yeah, this could be interesting too.